All right, today we are diving into one of the most powerful and maybe one of the most misunderstood pieces of tech behind modern AI, the vector database. You know, these things are the secret sauce, the reason AI can sometimes feel like it actually gets you, and we're going to break down exactly how they pull it off.
So, let's just start with the big question, right? For years and years, search has just been about matching keywords. You type cat, you get back pages with the word cat. Simple. But how does a computer get past that? How can it possibly understand what you mean, the whole vibe of your question, not just the words you typed? That's the magic trick we're about to pull apart.
So first up, the magic of meaning. And I'm not kidding, we're going to start with an example that feels way more like a magic trick than it does computer science. Okay, so imagine you've got a database full of different kinds of weapons, and you type in this search query, a weapon from Japan. Now notice what we're doing here. We're not naming a specific sword or anything, we're just describing an idea, a concept.
And bam! This is the result you get back, odachi, which is a type of long Japanese sword. Now here's the crazy part, the part that feels like magic. The original description for the odachi in the database, it might not even have the word Japanese in it anywhere. So how did it figure that out?
Seriously, how did it know? If it's not just playing a game of keyword match, what on earth is going on under the hood? Well, this right here is the superpower that vector databases give us. The ability to search by what something means, not just what it's called. And the secret, well, it's not magic, it's math.
And that brings us to the secret itself. What are vectors? This is really the key to understanding meaning. See, the answer is all about converting everything, and I mean everything, words, pictures, sounds, into a kind of universal language that computers get. And that language is math. The format is a vector.
So what even is a vector? Don't let the fancy name scare you. It's really just a list of numbers. That's it. Think of it like a unique numerical fingerprint, or even the DNA for a piece of data. Each number in that list represents some deep core feature of the data, capturing its essence in a way a computer can crunch. And this process, this act of creating that numerical fingerprint, it's called embedding. They're these really specialized AI models, embedding models, whose only job in life is to take a piece of data, whether that's a sentence, a photo, a song, and translate it into one of these incredibly powerful number lists, one of these vectors.
Now, this is a great way to make this whole abstract idea really concrete. Let's say an AI model looks at the word king. It might break it down into concepts like gender, wealth, and power, and give it a vector like 111. A queen, well, that's really similar, right? But different on that gender axis. So maybe her vector is 010.7. A man has less wealth and power, so his vector is different again, and so on.
And here's where it gets really cool. When you do this for millions or even billions of pieces of data, something amazing happens. Things with similar meanings naturally end up as mathematical neighbors. King and queen get clustered together. Dog and puppy are side by side. Car and truck are in the same neighborhood. The data literally starts to organize itself based on pure meaning.
Okay, so now we have all our data neatly organized in this giant meaning space. Everything is clustered with its relatives. So the next logical question is, how do you actually find anything in there?
Well, it's actually this surprisingly elegant three-step dance. First, your search query, remember, a weapon from Japan, it gets turned into its own vector using the exact same AI model. Step 2, the database then calculates the mathematical distance from your query vector to every other vector it has. And finally, step 3, it just returns the ones that are closest. Its nearest neighbors. Simple as that.
But what does closeness really mean here? There are a couple of popular ways to measure it. Cosine similarity is a big one. It doesn't care about the length of the vectors, just the angle between them. If they're pointing in the same direction, the angle is tiny, and they're considered very similar. Then there's Euclidean distance, which is easier to picture. It's literally the straight line distance between 2 points, just like finding the closest coffee shop to you on a map.
Okay, so we've got the theory down, but if you're actually building something, what tool do you use? I mean, the world of vector databases is absolutely exploding right now, and picking the right one for your job is, well, it's pretty critical.
And this really lays out the different tiers of tools you've got.
If you're just starting a small project, maybe under 1 million vectors, something like PG Vector is fantastic. It's just an extension for PostgreSQL, a database you probably already use. Super simple. But as you grow into the tens of millions, you'll need a dedicated engine like Qdrant, which is built for raw speed, or Weaviate, which is great at mixing keyword and vector search. And then, for the really big leagues, hundreds of millions or billions of vectors, you need an enterprise-grade powerhouse like Milvus.
So you see, at the end of the day, there's no single best database. It's not one size fits all. The right choice really comes down to asking yourself these key questions. How much data are you really talking about? How fast do you need your answers? And honestly, how much complexity can your team handle right now?
Okay, let's zoom all the way out now. We've talked about the what and the how, but why is everyone so obsessed with this technology right now? Why has it become one of the most important building blocks for AI? It's because vector databases give large language models, or LLMs, something they desperately need: a memory, a reliable, long-term memory. You see, as amazing as models like GPT-4 are, they've got some major flaws. For one, their knowledge is stale. It's basically frozen in time at the moment they were trained. 2, they know nothing about your private internal company data. And 3, and this is the really dangerous one, when they don't know an answer, they often hallucinate. They just make stuff up that sounds completely believable, but is totally wrong. The solution to all these problems is this powerful technique called retrieval augmented generation, or just RAG for short. It's kind of a fancy name, but the idea behind it is brilliant and simple. Instead of forcing the AI to answer from its flawed memory, you let it cheat. You give it an open book exam, providing it with the exact, relevant documents it needs to find the right answer. And here's exactly how that works in practice. So, a user asks a question, but, and this is the key, before that question ever gets to the big AI model, it first goes to our vector database. The database does a quick similarity search and pulls out the most relevant, up-to-date information. Then, it bundles the user's original question, plus all that fresh context together, and sends the whole package to the LLM. The model now has everything it needs to give a smart, accurate answer based on facts, not guesswork.
So the bottom line is this. RAG, with a vector database at its heart, effectively gives AI a perfect, searchable, long-term memory. It's a memory that you can load up with your private data, your company's knowledge base, and that makes the AI so much smarter, so much more useful, and frankly, so much safer to use for real business problems.
And this all brings us to the big debate that's happening in the AI world right now. Is this whole RAG setup, is it just a temporary patch? A clever hack we're using while today's AI models are still a bit limited? Or are we looking at a permanent, fundamental piece of the puzzle for how we'll build intelligent systems for decades to come? Answering that question, well, that's the billion-dollar bet the entire industry is making as we speak.